Good day. Electric fields. You can't see them, you can't taste them, you can't touch them, but you can detect them. The only time a human can really detect them, and this is really not a good situation, is if you are outside and it's about to strike lightning literally right in your area, like near you. The hair on the back of your neck and maybe on the back of your head will start to feel tingly and stand up. Not a good place to be. What they did install in our school, the Thor guard, for lightning detection for during football games and soccer games and whatever games we have out of the field. That is an electric field sensor, and that goes off and screams really loud. It has a little horn because there's a sensor there that can detect the electric field. So I'm going to compare electric fields to gravitational fields because in many ways they're similar, but in many ways they're not. So first of all, an electric field is the area surrounding a charge. Now you did the virtual lab and you drew lots of pictures to show the shape of the field and used a little sensor to sort of measure the strength of the field. So there's some comparisons. In electric fields, the force that would happen to work on a charge is equal to the electric field strength times the value of a charge. And this is generally a small q. I'm going to box this one because we're going to include it on our formula page. For force between two charges, it's a lot like gravitational. We have a constant. We had a constant. I use big Q and little q, but again, it could be just Q1 and Q2 over d squared, which we already have for Coulomb's law. We learned from Newton that mass times gravity on Earth is equal to the force between the Earth, an object on the Earth, and the radius of the Earth. The same thing happens in electrostatics. This EQ is the force. It's also equal to K big Q Q over d squared. And in the same case as here, the m's will actually cancel, leaving us the value of gravity. Here, the q's will cancel, and we can find the electric field strength of just a charge. And I used big Q. This is one we're going to have. So think of this is like Earth, right? Things drop to Earth. And they're at the surface of the Earth, G, 9.8 is the value. As you go farther and farther away, it gets weaker. But this is only good for at the surface of the Earth. And that has to do with us dropping things near the surface of the Earth. This force is like a charge, okay? This is the strength of the field, kind of like gravity. And the charge would be like the mass. This would be testing. So it'd be like, if I have a big charge, it could be positive or negative, and then I have a little charge, and we look at how it behaves, and that would be the force. So it's a similar. As we go through Coulomb's law and Newton's laws, we see that we can do the strength of the field. G, we don't call it the strength of the field of the Earth, but it is. And that strength of gravity changes as you go farther and farther out, because as you go farther out, it gets weaker. The same thing happens if I have I'm just going to put a big Q in these. So I have a big charge, call it Q. Could be positive or negative. Just like on Earth, when gravity's strongest at the surface, it's going to be strongest at the surface. And you should have found when you used the little sensor in the lab that the field strength was always stronger when you're right on top of the charge. But when you get farther away, it gets weaker. So that E is the strength of the field, the same way gravity is the strength of our field. We just think of gravity always being on the surface. We don't think about the fact that we can go into space, or objects can go into space and the gravity will be weaker, but it's more common to think of that here. All right, electric field strength is measured in newtons per coulomb. If you were to take this formula, I'm just going to draw on here. You don't have to necessarily write this. This is newtons equals E times coulombs. So if I divide both sides by coulombs, that's how I get newtons per coulomb. Force is still in newtons. The test charge is in coulombs. The big charge is also in coulombs. Going to add that in here. In this case, we're going to always consider big Q as like a planet making a field, and little q is like the tester, like the little sensor. Or if you think about us, you know, dropping an apple around the surface of the earth, those are the things we use to test. And think about this. Does the gravity of the earth depend on your weight? In other words, if you lose weight and you lose mass, does the gravity change? No. The only reason gravity would change is if the earth changed. So field strengths depend on the charge making it, not the charge testing it, and little q will be considered a test charge. So that's probably the only tricky part about this, is trying to keep track of whether it's making it or testing it. All right, so let's do a practice problem. It requires 10 newtons of force, so this is a force, to move a test charge, so that's going to be a little q. Remember, here's nano. Nano means 10 to the negative 9th. What is the strength of the field? Well, that means E. So we're going to use this one up here. F equals EQ. So we have 10 equals E times, and this is going to be 5 times 10 to the negative 9th coulombs. So I'm just going to divide both sides. So let me move this up, grab a calculator. Stick right here. So 10, I guess I have to turn on clear. 10 divided by 5 second EE negative 9. And there we get 1, 2, 3, 4, 5, 6, 7, 8, 9. So E equals 2 times 10 to the 9th newtons per coulomb. Second example, what is the electric field strength of a 15 coulomb charge? So this is a positive, but it's also a big Q because it's not testing it, it's creating the field. And this is a D. So that means we're going to be using this formula for the electric field strength. So we're going to use E equals, and it's the same Q, or excuse me, the same K as in Coulomb's law. All right, so 9 times 10 to the 9th, 15 coulombs is a ridiculous amount of charge. It's like a lightning strike. I'm just using numbers that are easy for the math. And 2 squared. All right, so 9 times 10 to the 9th times 15. I always like to hit equals, that's just me, divided by 4, because 2 squared is 4. Okay, I'm going to make that 3.38. So E equals 3.38 times 10 to the 10th newtons per coulomb. So the tradition for drawing a gravity field would be testing which way would something fall. Oh, it always goes towards the earth. Well, when you have positive and negative charges, someone a long time ago decided you had to use a positive test charge. And so that's why this has to be a positive small test charge. The reason we test with small objects is we don't want to actually add to the field or make it different. So test charges are always positive and they're always small so as to not interfere with the field. The field lines move from positive to negative, and we're going to turn the paper over and we're going to draw some pictures. Fields are vectors and they add like vectors. All right, so we're going to draw pictures. The reason I'm going to draw these pictures is they're going to look a little different than your virtual lab, and I want you to see what they would look like, say, on a test. All right, so just turn your paper over. Just use the back. Let's do field 1, positive charge. Well, what way would a positive charge go? If I were to put little positives here, they would all repel. That's the first field. Second field, a negative charge. Well, you have to use a positive tester. They would always attract. That's why this one looks the same as gravity of the earth. All right, let's go to a third field. A positive and a negative. And again, we're just assuming they're the same size. Again, they would, excuse me, a positive charge would attract. We know there's some bending that happens here. Some of us saw that more than others. Get our arrows straight. And then we would have a few arrows coming in here. And we would have a few going out. That's our simplified version of, and again, the way you would have to look at them on a, and again, you always have to remember, how do the arrows go? The way that a positive would travel. If I put a positive here, it would go plus to minus. Okay, field 4. if we have two positives, there is a repelling. I'm just going to draw the basics of this. We're going to simplify the pictures. And of course, there would be some straight out ones here. Let's go to the fifth field, because there's 6 altogether. 2 negatives. So it's the same shape, except your arrows are going to be reversed. And yes, you're going to have to know all these. And yes, there are pictures of these on the test for you to figure out. That's why we're drawing them again. And then, so there's a special spot here. I'm going to use a highlighter. I'm going to use a little dot. That yellow dot, can you see the yellow dot? Yes. The special thing about the repelling fields, in the center, I'm going to make a little arrow here. Inside is 0 field strength. So maybe you did or maybe you didn't when you use the virtual lab and you use the little sensor. Yes, you go on top of the charge, you have strong field. And yes, if you go far away, you get a weak field. But there's a 0 point in the middle of these where they repel in these particular fields. That is still a 0. Okay? And let's just call it what it is. Numbers 1 through, well, let me do the last one. We'll just do the last picture and then we'll go through them all. All right, number 6. The last one was the lines of charge. And we usually use a little line. This is the idea behind a capacitor. We'll talk about more of these later. And again, this one had a basically straight, except till the end, they get a little bit of curved direction. Okay, so this one, let me see if I have a different color. I'd love to use a different color. Okay, I'm gonna use this. This one is considered uniform. It is called a uniform field because it is essentially the same in strength all the way through. Now, I'm going to zoom out because all of these are considered non-uniform. They're not the same strength everywhere. Lines are closer and farther, okay? The other thing that we need to recognize, so here's blue, is that these lines, all of these lines are called lines of force. Doesn't matter, I'm counting, you can point to all of them, it doesn't really matter. All of these lines we drew, whether it's in the uniform or the non, are considered lines of force. Okay, so more lines and closer equal strong, okay? And less, lines and farther apart equals weaker. So basically, we have 0 strength here. These are far apart, so that would be a weak part of the field. These lines are really close, so they would be stronger. If I go to these, same amount of lines, but if you look in closer in, they're closer, farther out, they're weaker. All right, so they're called lines of force. These have a 0 field, and anytime they're closer or more, they're stronger, farther apart, they're going to be weaker. Okay, that's it for today. You have some work to do. Peace.